It turns out that permutations are extremely interesting mathematical objects with a lot of properties hidden below the surface. One of these is the so-called sign or parity of a permutation, which we're going to learn about in this video. Now, you're all familiar with the parity of an integer. Parity means whether it's odd or even. And every integer is either odd or even, and there are some properties to do with adding integers and their parity. For example, odd plus odd equals even, odd plus even equals odd, even plus even equals even, and there's another one as well. So it's slightly surprising that this notion of odd and evenness can be extended to permutations as well, with a similar rule for composition as we've just seen for adding integers. So to begin with, we're going to define a transposition to be a two-cycle. It's just another word for a two-cycle. So a permutation which swaps two different things, I and j, and leaves everything else alone. And we now have the following lemma, which tells us that every cycle can be written as a product of transpositions in a particular way. So if you have an m cycle, a0, a1 up to am minus 1, then that's equal to the composition a0, a1, a1, a2, and so on up to the final two cycle, am minus 2, am minus 1. For example, this result is claiming that the 3 cycle 1, 2, 3 is equal to 1, 2 composed with 1, 2, 3. So it's a good idea to pause the video and check that that's really true, and that it's also really true that the 4 cycle 1, 2, 3, 4 is equal to 1, 2, 2, 3, 3, 4. Another thing to notice about this lemma is that it's expressing an m cycle using m minus 1 transpositions. Anyway, let's see why this result is true. So the proof is by induction on m, because for m equals 2, which will be the base case for our induction, it's completely obvious. The left-hand side when m equals 2 is just the permutation a0, a1, so the 2 cycle a0, a1, and the right-hand side when m equals 2, again, it just has the single transposition a0, a1. So when m equals 2, the two sides of that equation are literally equal, and there's nothing to prove. Now let's do the inductive step. So we're going to assume that the result is true for m and prove it for m plus 1. So the product that we have to work with is this equality when you replace the m by m plus 1. So on the right rather, you would have the product a0, a1, a1, a2, all the way up to am minus 1 am. But if you think about just the first set of, all of the terms in that product except the last one, then the inductive hypothesis would tell you that the product of the first m minus 2 terms there would be this m cycle. So all we have to do in our inductive step is to prove that that m cycle times the final transposition am minus 1 am is equal to the m plus 1 cycle a0, a1, a2 up to am. So what we have to do in our proof is just think carefully about the composition on the right here and prove that that composition is actually equal to the m plus 1 cycle a0 up to am. Let's write this down. So in order to do that, we'll simply think about what that composition does to each possible number. So first of all, let's think about an ai where I is less than m minus 1. We're asking, what does the composition, which I've put in the box there, do to ai if I is less than m minus 1? Well, okay, first you have to do the 2 cycle on the right, am minus 1 am. That doesn't move ai because ai doesn't appear in that cycle. So that 2 cycle sends ai to ai. Next, let's think about what happens to ai under the cycle a0 up to am minus 1. Well, that will send AI to AI plus 1. A0 goes to A1, A1 goes to A2, and so on. So this AI will go to AI plus 1. Okay, so we've established what the composition on the right in the box does to AI if I is less than m minus 1. So now let's think what happens to am minus 1. So the 2 cycle am minus 1 am sends it to am, and the m cycle a0 up to am minus 1 sends am to itself. Remember that in a cycle all the numbers have to be different. So am is not one of the numbers in that m cycle a0 up to am minus 1. That means the cycle sends am to itself. So the m cycle a0 up to am minus 1 doesn't contain am, so it sends am to itself. In summary, am minus 1 is sent by this composition first to am and then to am again. Finally, let's look at what happens to am. The 2 cycle sends am to am minus 1, and then the m cycle sends am minus 1 back to a0. We now know what our composition in the box does to any AI, and let's think about what it does to a number which is not equal to an AI. Well, both of those cycles only move the AIs and they send everything which is not an AI to itself. So any number which is not an AI is sent to itself by this composition. So we've seen that each AI goes to AI plus 1 for I less than or equal to m minus 1. And we've also seen that am goes back to a0. But what I'm just describing is precisely the m plus 1 cycle a0 up to am. So that composition on the right really does equal to the m plus 1 cycle a0 up to am, and we've completed the inductive step in our proof. What this result allows us to do is to prove a more general theorem saying that every permutation is equal to a product of transpositions. We saw on the previous slide how to express a given cycle as a product of transpositions, but what we know is that every permutation can be written as a product of disjoint cycles. That was the theorem from the previous video. So if we start with a permutation, express it as a product of disjoint cycles, and then use the lemma we just proved to express each of those disjoint cycles as a product of transpositions, then we've expressed our original permutation as a product of transpositions. So for example, if you have this product of cycles down here, then you can express that as a product of transpositions just by using the result from the previous slide twice. So 1, 3, 4, the 3 cycle is equal to 1, 3 composed with 3, 4, and 2, 5, 7, 6 is equal to 2, 5 times 5, 7 times 7, 6. So that expresses that product of 2 cycles as a product of transpositions. Finally, we're ready to define the sign of a permutation. So here's the definition. A permutation is even if it can be written as a product of an even number of transpositions, and odd if it can be written as a product of an odd number of transpositions. And the second part of this definition is the sign of a permutation. So the sign of a permutation f, which we write like this, is 1 if f is even and minus 1 if f is odd. So here are some examples, starting off with the identity permutation. You can write the identity permutation as 1, 2 times 1, 2. That's a product of an even number of transpositions, so the identity is even. Equally, if you look at this permutation, 1, 2 times 2, 3, then that's even. Of course, 1, 2 times 2, 3 is equal to 1, 2, 3. So the 3 cycle, 1, 2, 3, is an even permutation. And in fact, if you return to our slide right at the start where we expressed an arbitrary cycle as a product of transpositions, you'll see that we expressed an m cycle using m minus 1 transpositions. Now, m is even if and only if m minus 1 is odd. So what that shows is that odd length cycles are even and even length cycles are odd. For example, 1, 2, 3, 4, an even length cycle will be an odd permutation because it equals the product of the 3 transpositions 1, 2, 2, 3, 3, 4. Right, we can say something about the sign of a product, which is just like the result about adding even and odd integers. So I mentioned at the start that, for example, even composed with, so an even number plus an even number is an even number plus an odd number is an odd number, odd plus odd is even, and so on. The same sort of thing holds for composing even and odd permutations. So let's begin by making an observation. If you have a permutation S and you express it as a product of transpositions t1 up to tk, then the sign of S is minus 1 to the power k, because the sign is supposed to be 1 if k is even, and minus 1 if k is odd. At least let's be slightly more careful about that. S should be even if it's possible to find an even number of transpositions whose product is equal to S. So if you can express S as a product of k transpositions, then the sign of S should be minus 1 to the power k, because if k is even, then minus 1 to the k will be 1, and if k is odd, then minus 1 to the k would be minus 1. So the lemma says that the sign of a product, a composition, st, is equal to the sign of S multiplied by the sign of t. So the sign of S is a number and the sign of t is a number, and we're just multiplying those numbers together, whereas this st means the composition of the permutations S and t. But the proof is really just easy, because if you can write S as a product of k transpositions and t as a product of L transpositions, then you can write st as a product of k plus L transpositions, just by writing those transpositions which equaled S and the transpositions which equaled t side by side. That gives you an expression for S composed with t using k plus L transpositions. So minus 1 to the k, that's the sign of S in this case, and minus 1 to the L, that would be the sign of t. And as we've just written, st is a product of k plus L transpositions. This thing is the sign of st. Okay, so perhaps you've noticed a big problem with this lecture, a really big problem, which is that it's not really obvious that the concept of the sign of a permutation makes sense at all. I mean, that is, what if I could take a permutation and write it both as a product of some collection of an odd number of transpositions and as a collection of some even number of transpositions? Then that permutation will be odd and even at the same time. And this sign function wouldn't even make sense, because it would send the same permutation both to 1 and to minus 1. Functions aren't allowed to do that. So we have a big problem. None of this lecture makes any sense at all unless we're able to prove that every permutation is either odd or even, but not both. That's the subject of the next video.